like, I don't have a great answer for this, but I know people have found instances where you can generate some data set that has some T-closest property and still kind of somehow figure out how to identify certain key things that you said you shouldn't have been able to identify. So sometimes, I think sometimes they're using other sorts of data sets to break it. Sometimes they're looking at the statistical properties and they can say, with certain probability, I can probably say that this person has some private traits. There's all. So this paper, I think, is the least cited, has been cited like 700 sometimes. So there's been a lot of work on this topic. But this was a line of reasoning that has kind of dried up. So this is not so much how people look to do this anymore. So before I talk about the next kind of the new way where people have kind of tried to preserve privacy, which is called differential privacy, which is this allows us to relate back to the noise problem. I'm going to talk a little bit about the Netflix challenge and kind of see how with the secondary data set you could also break, there are problems with the Netflix challenge. So okay, so if you haven't heard of this, so Netflix is this way where you can rent these videos either through the mail or mainly, I think, so online now, and people would rate how much they like the video, and Netflix wanted to recommend other videos for you to watch. And they figured this was worth doing a very good job of, and they had a small team of people trying to build a recommendation engine, and they had done so well, but they're like, we'd really like to do better. Let's try and crowdsource the kind of research from universities to kind of build us a better recommendation engine. Okay? And so what they did is they released a really cool data set. So there was D1, which had the, so let me see what is in here. So this was in 2006, so it had a user, so every data element had a user ID, it had a movie, it had a date of grade, and it had some grade, it had some grade of the movie, and then they released D2, which had user ID, movie, and the date of grade, and but this one did not have the grade. So you're supposed to predict how well these users would grade this movie on this date. Okay, and Netflix also kept another data set, D3. They were smart about this. And so, and these were like really large data sets. These were like, how many records were these? I forget how big these were, but these were like some of the largest labeled recommendation problems available at the time. And so they kept this D3, so researchers would try and build some sort of recommendation engine using D1 and test it on D2 and to try and see how well it would work. Or they would, and then they would also, so they kept this data set D3, which they of course have the grades for, but they did not have the user ID movie or the date of grade, and they used this to cross-validate. So they would use these were public, and this one was private. Okay, but this wasn't private in any interesting sense. So they used this one to score how well the recommendation engine is built on these two And so if you improve the recommendation by more than, I think, by more than 10% on this hidden D3 data set, then they would give you $1 million, right? So like $1 million. So this caused a lot of great research. There was, I think, over a year or two. Eventually, there was a group that I think got to like 9.8 something percent by the deadline, but they reached the 10% sometime soon after. Got the money, but they wrote it was a big it was a really big success for machine learning. A lot of cool research came out of this, and people realized how to do this really well. But then there was a problem. So it doesn't seem like there's much that could really go wrong here, right? Like, what is possibly bad if someone didn't want to grade a movie, then they didn't have to grade it, right? So and in fact, most people did not so people kind of may have graded movies on here that they didn't want people to know about. Okay, so what happened is people who watched a lot of movies and tended to grade them. Well, there's also another movie database out there, very public, so the Imdb, right? So there's this internet movie database, and so this has user IDs associated with it, and you can identify some people based on their ratings on Imdb. But this was kind of understood to be public, so people only rated movies that they were okay with other people knowing that they had rated. And they usually rated them on, on a similar date, right? Because they just watched them on Netflix. And so some people would watch some, maybe certain adult movies, but they wouldn't post the reviews on IMDb, but they might do that on Netflix. So there was a group of researchers came and said, we can identify some large fraction of these users by their username on IMDb and find out other movies that they've also watched and graded. And so a bunch of users were not too happy about this, and there was a lawsuit against Netflix. This lawsuit was eventually dropped. But the downside of it is Netflix was preparing to issue another challenge, which would have released a whole lot of new data with more features and so forth about it. But they ended up canceling this because of all these privacy concerns. They couldn't figure out how to release the data so that it wouldn't allow people to kind of cross-reference the data in here with other data sets and kind of uncover, which user was which and which movies they were watching. So they ended up canceling this and not releasing this other data set. So that was really too bad. There still are lots of data sets that companies have released. So if you go back to like Google and Facebook and Yahoo, they want researchers to help them figure out how to advance the state of the art here, use kind of the collective kind of academic research. So they've released a lot of data sets. They've tried to anonymize them in various ways. Often they do it it's a very small subset of their full data set. So if you use one of these, you don't get the full data set that they have access to. But that's kind of their way of doing it. And whether it's really anonymized, well, I don't know if so I know Google and Yahoo have a lot of really nice public data sets. I don't think any of those have had any issues with them. They've been pretty careful, strictly on information, but most of the work people have done has been more on how do certain algorithms scale. They have been able to make useful predictions that would allow an academic to kind of understand how to post ads on a website. Most of that research which is really their core challenge and their core business it's done inside those companies because it's so hard for independent researchers to kind of get access to kind of the personal information they need to kind of be able to understand these sorts of issues. Okay, before I put the screen away, there's one more thing I wanted to show, is that, so one important issue when dealing with any sort of medical data, and I think this is partially in reaction to this study and some of these other issues, is that there are these very stringent rules that if you're going to publish a research paper, and most journals will only accept a paper if it has clearly said that they follow certain policies that have been laid out by, say, National Institutes of Health about how can you collect and use medical data and patient data in research studies. And it's a really complicated set of rules. It keeps going on. So there are a couple of things. So either you have to, if you read the second point here, the names or other specific identification of persons or class of persons authorized to make the request use of disclosure. So let's see. One of these things, there's one of these constraints which looks a lot like the Kane anonymity constraint. They haven't even gone to the L diversity and T closeness. They just say that certain traits need to be anonymized, but they don't really clearly define exactly how to do this. But there are other things that they'll ask for. They'll say that patients need to be made very clearly aware of what that the data is being collected for a study, and that they understand all of the uses that it will be used in. Okay, so they said, we're going to use it for this specific study. So the downside of this is you can't collect a data set and then use it over and over again for lots of new studies. You can use it often for one specific study, then you have to recollect it over again. And so, this is, as I think for the most part, this has protected a lot of kind of stuff from coming out, but it's really made it very difficult to get any large sort of patient data sets for this. And so from anyone who's tried to work or tried to, any of your project in this class you want to do on medical patient data, you probably found a hard time actually getting it. So there's there's some group working with this company that has some sort of health records, and they've been anonymized in a certain way, and sometimes in strange ways, and maybe you maybe understand where some of these weird numbers have been coming from now. There's kind of a lot of hoops you have to jump through in order to use this, this sort of medical data in research. Okay. So let me try and talk about differential privacy. Differential privacy. Okay, so the conceptual idea here is, instead of thinking about one data set that you want to have some properties, we're going to think about potentially two data sets. So there are two different data sets that, and you're gonna put one of these data sets, make it public or make it accessible in some way. So that has two properties. So one is that D1, and there's some distance function between D2, and so this is going to be, is small. So formally, I'll try and define this a bit, kind of the formal definition, but often we'll say this distance is like 1 between them. So think of, there's one data element which has been changed. Okay, so let's say the data set contains your personal information, or or the data set does not. Okay? So these data sets are very close to each other, and so you want them to be close. So this you want this to imply that the global analysis is going to be similar. But you also want another property that so you can't identify individual data pair. Okay? And so I need to specify this a bit more. But the idea is, you kind of said that there's another one which is close to it, which has some data point that's been changed. And it's going to look pretty much similar, and you don't know which one of these it is. So you don't know if your data set, your data point describing you is in here or not. Okay, and you, so you can't be able to identify. So this should mean that the probability. So let me try and write down a formal. So I'll try and define this formally in a second. But the general idea is you're going to take the original data set, and so then this is equal to D2 plus so some amount of Laplacian noise, operated 1 over epsilon. So you've taken a data set and you've added some noise to the data set, so that they're close, so their global analysis is similar. But because you've added the noise in a certain way, you can't know for sure anything about any certain individual data point. And there's some probabilistic ways that you can have some guarantees. So there's several ways to kind of try and specify this, and I'll go through some examples. But the classic and kind of the bare bones way of defining this is that, so D1, which you start, is going to be so it's going to be n, n bits. Okay, so this is 0, 1 to the power. Okay, and so think of this as you have n people in the database, and the 1 bits are the ones are the people who have cancer. Okay, so you want to, and so you being in the set that has cancer is you're corresponding with the ith bit, and if you have a 1, then you have cancer. If you have 0, then you don't. Okay, and so D will be close to here, and so we're going to consider D1, and we're going to say that the distance between D1 and D2 is going to be equal to 1. So that means that they only differ these are only going to differ in a single bit. Okay? And so if they satisfy this condition, and you're going to have some, and for a class of questions, so you have a class of questions you can ask, and this question will be like, let's look at a subset of the data set and say, who is, so think of a Q in this class is actually defining, a certain subset of that. This is equal to a of the set. The set 2 there. Okay, so then what you want is that the probability that let's see that the query on D1 is in some range. So is in, say, is greater than, say, 0.5. So let's say this is, say, is greater than say 10, so more than 10 people in some query range, over the probability that the same query range on D2 is also greater than 10. So this 10 is for, so this can be for any value. Then you want this to be less than 1 plus epsilon for some epsilon parameter. And if all of these conditions hold, then this is called epsilon differentially private. Okay, so let's look at this a little closer. So if I want to say, for any class of queries, the probability that that this query, this subset of people, say all the people in a certain zip code, there are more than 10 of them who have cancer. On dataset 1 and dataset 2, I've said it's been released with this sort of noise. So I know the noise model. I know it has this noise model. The probability this is greater than 10 divided by this is off by some fraction. Right? So if this is maybe this could be a fraction off by, if epsilon is 1 here, then this is off by a factor 2. This one is no more than twice as likely to have more than 10 people in this range have cancer as this data set. So that's if epsilon is 1, then this fraction is 2. Right? So actually what they'll write is this is e to the power of epsilon, and this is roughly, the math works out when you use e to the power. And that's why you use this Laplacian noise. So a Laplacian random variable is kind of like a Gaussian random variable, but it's not squared. So the Laplacian noise is e to the minus epsilon with some constant in front here. So Gaussian would be e to the minus epsilon squared. This one, it looks kind of more pointy, but it ends up giving you this sort of property. Okay, so so the idea is if you add noise to the data set in a certain way, so that means essentially think of for every bit, there's some probability I'm going to change the value of the bit. Okay? So I want such that if I want the probability to be small enough that there will be two data sets which are going to be close to each other. But I want it to be large enough so that the probability that there's a queries return some answer, maybe this is greater than 1, so there's one person in there with this trait. That these are going to be very close to each other. So by telling you the noise, then you know, okay, this is noisy, so I know how much I can trust the data. And this tells you kind of how much you can trust it, or this also does, but it's revealing individual, it's for certain queries you can ask, you can't be too sure about any. So it allows you to ask some larger size queries and know fairly accurately what the values are, but not too accurately that you can identify individual people. So on the larger the query, this is a relative error and you get some sense of what's going on, but not too much. Okay. So it's a little hard to wrap your head around. So I'll go through some slightly more specific scenarios. But before I do that, there are kind of two approaches to doing this. Now, notice I had to restrict this class of questions in some way. If I was able to ask any question I wanted to, I might be able to deduce certain things. Right? If I know that the data sets are really close, I might be able to figure out that there's a pretty good chance that someone is in the data set, right? So if I could ask queries on individual people, maybe I could reveal too much information. So you often have some condition on the class of queries you can ask. And this will vary on the scenario. And there are two kind of general approaches to this. There's the interactive way, which is allows you to get stronger guarantees. And so this is where your data set, the original data set, is hidden behind some sort of firewall. Okay? So you're holding onto the data set, but you allow questions, right? So you could set up some sort of database and allow some queries on there. And so you can see which questions are being asked. You can return answers. Right? So one thing that this allows you to do is to not have to actually scramble the data set itself, but to do something like allow questions and then return the true answer to the query, but then you return it with this sort of noise. So every time you return it, you add noise onto it. So instead of adding noise to the original data set and kind of putting this out there, you kind of restrict the interaction with it. Okay, so you have to be careful. So if someone keeps asking the same question over and over again, you have to be consistent. Otherwise, the chance of adding this noise, you can probably figure out what the true value is. So this is why you put behind the firewall. You allow questions, but you may have to limit the questions. And if you don't allow individual queries, you allow sort of larger queries that, again, you can obscure the answer with a small amount of noise. And so you have to do one of two things. So you either have to be so you either have to have an upper bound on the number of questions. So basically, you put some service out there. It's like a game of 20 questions. After they've asked 20 questions, they can guess, or the game's over. So there's only so many questions someone can ask. This seems like it's not quite as good as putting a data set out there for someone to really study. One of the other things people have done is that you need an exponential number of questions to statistically recover useful information. So if you ask enough questions, you'll be able to recover, but it's somehow exponential in the size of the database. So it's kind of assuming P is not equal to NP, assuming some of these hardness results about computing, you need to solve an NP problem to pose a sub-exponential number of questions and recover some information about it. So then you can kind of put this out here and say, it's going to be too hard for someone to actually do this, even by some brute force approach. Or maybe you make the response rate slow enough and so on. Okay, so but this is kind of still weird. It's kind of interactive behind the firewall. So this is less desirable. There's also this non-interactive way. And so this is probably what you had in mind, where you take a database and you actually put so D plus this Laplacian noise, and you make this public. Okay, and so when you do this, you kind of have to you kind of have to hope that there's no side channel attack. And it kind of, it should kind of prevent about here, but you can say, well, if people released a lot of these databases with the same information, each of them with Laplacian noise, enough noise, maybe you can recover it, but maybe I'm the only one who has this information, so I'm not worried about some sort of side channel attack. You still need to be careful in certain ways about this. Okay, so let me try and give a more concrete example of how this would work. So So here's a piece of kind of closely guarded but also obfuscated piece of information. Or, you know, maybe you don't know the answer to this. So how tall is Sylvester Stallone? Does anyone know the answer to this? So you can look it up online even if you want to. But so it's actually probably not going to help. Or it's probably helped some. But there are whole websites devoted to this, trying to figure out, trying to figure out how tall he actually is. And there are various photos of him next to other people. Is he actually this tall or not? So there's certain, at some point I looked into this, you know, I don't, kind of procrastinating about something. And it seemed like there was good reason to believe at some point he was only 5'6". Okay, but he of course wants people to believe he's taller. He's an action hero, right? And then there's stories that maybe he had surgery to actually become taller. I don't know what happened. Or he goes through lots of things. Always has lifts in his shoes in certain ways whenever he's out. So I'm not sure what's going on. Okay. So I'm not sure what his actual height is. It's somewhere between probably 5'6" and 5'10", right? So he's between 66 and 70 inches. Maybe he's even 72 inches. Maybe he'd like you to believe he's 6 feet tall. But let's say he wants you to believe there's a chance he's 5'10", he's 70 inches tall. So our database is going to be D, is going to be just a single value. Okay, so D, maybe his true height is 66. And I've released a data set with some amount of Laplacian noise. And I don't know what his true height was. And my noise may have made this larger or smaller. And I released the data set that said he was 67 inches. Okay, so now I want to look at the probability given that D is greater. Let's see, let me write this up. That D is greater than 70, right? So the probability is greater than 5'10". Okay, and so actually, given this for D, given this amount of Laplacian noise, you can say that this is going to be about e to the minus 2 epsilon. So epsilon is some parameter I can put based on how much noise. So maybe it was a little bit smaller. So I can also look at the probability given that D1 is going to be greater than 70. And this is, so it is, okay, so I could have released, I could have released D2 or I could have released D1. Okay, so if I released D2, then the true height, okay, so the true height D, the probability D was greater than 70. So if I released, so this is given, let's say it's 68. I think I have in mind. Yeah, okay. So this is closer to the example I have in the notes. Okay, so say that I release two database 68 inches or 67 inches. Given those 68 inches, the probability D is greater than 70 is e to the minus 2 epsilon. Given I release D2 at 67, it's e to the minus 3 epsilon. Okay, so if I look at the ratio between these two things now, the ratio between these, this ratio is e to the minus 2 epsilon over e to the minus 3 epsilon, and this is about e to the epsilon. Okay, because I can add these. Yeah, so that, and this is about 1 plus epsilon. Okay, so the difference in the value here was 1, and the probability that is greater than 70 inches, given this information, where these distances are 1 apart, is off by 1 plus epsilon, given I've added this, this Laplacian noise, which has this property. So it has a property that the further away I get, it decreases exponentially at a rate controlled by this epsilon. And so you can kind of, if you go through and work out the math, you'll see that the ratios of these being above 70 are off by 1 plus epsilon. So maybe you can look at it other ways. One is the probability he's smaller than 66 inches. These are also are going to be the probability given these these data points are off by 1 plus epsilon. Okay, so there's reason to believe that people from his camp have released different evidence about his height and added noise to it in various ways. And hopefully they may think that they've controlled it so you don't know for sure whether he's above 5'10" or if he's below, 5'6". And there's some amount of probability that you're not sure about because of all the noise in all these this information you've got. Okay, so this is kind of the rough idea of how this works. So this was for a very simple database with only one value. Okay, and kind of given this same problem, you can think of kind of the problems with T closeness. If you look back at T closeness now, you said he may have been in some category of some set. So let's say there are a bunch of people. He was filmed in a scene that was in New Jersey. And he was filmed with a bunch of extras in New Jersey, and he's roughly the average height of everyone in the crowd. Okay, so it's enough to believe that he's at the same average height as someone who lives in New Jersey, as an average man in New Jersey. Okay, there are enough people in New Jersey that it satisfies K anonymity. There are a lot of people in the scene, so people of different heights